Hello everyone, so this is a follow-up video to my demo showing how my Wordle clone with SFML works. And so basically I'm going to break down in this video the core parts of the game and how they're actually handled within my code. So of course when you first enter the game you'll have this simple scene where you have the grid of the possible guesses, and then you've got the keyboard at the bottom, which is the input, and then just have some additional text on the side. So this entire window here is actually handled inside the puzzle window. So we have both the .h and the .cpp files for everything. So the puzzle window, which is here, this is encompassing the entire window, and so that includes a number of different elements. So the text that appears just up here with the Wordle and then by Peter Mitchell, that part is just drawn as part of the PuzzleWnd. And so the rest of it though is we have the GuessGrid here, which is all of these elements. So the GuessGrid is made up of a number of different puzzle letters. So we have the puzzle letter, and so every single one of these individual little squares here, these are all individually puzzle letters, which are initially set to an empty state. And so once you put a letter into them, then they will allow you to obviously check a combination and all that sort of stuff. So then at the bottom here, we have a group of elements as well. And so this group is actually the KeyboardWnd. So we have the KeyboardWnd associated with that entire group. And then each of these individual elements inside of the keyboard, each of these individual buttons are attributed by the button file. And so they're very, very similar to the way the puzzle letters work, except that they also have information to be able to tell it what the button's action is, and to also just have slightly different state information. But essentially the button and the puzzle letter are very, very similar. So once we have the game played through, so this is obviously the actual live version of the game, so as we enter in, we would get our output, and so we can then sort of obviously try and guess what it would be. So in guessing what word we want to do next, we could, for example, do thins, and we can see we actually got two matches here. So the next word we can enter, if we try tombs, we've got a second letter. So then we can try torts. Still didn't get any sort of match. What else we could try? We could try tufts. No, tufts wouldn't be valid. We could try tours, and that's obviously not correct. So it doesn't have a U. Could do tolls, maybe. And we did not get it. So it was topos, which I was not going to get, obviously. Alright, so you can see here we have the other different screen. So regardless of not actually getting it correct, so we can now look at how this other screen is made up. So the entire larger screen here is obviously appearing as an overlay. So the overlay extends over the entire area, and so that is actually represented by the PostGameWnd. So this information is being represented as another sort of set of elements very similar to how it was for the other back elements. But you can see obviously that we can get some see-through here, so we can actually see some of the content. Now, the actual sort of box that's here, this is rendered by the PuzzleWnd, so it's just added as a background. You could have it sort of visually taking up the entire space, but for making it look nice, with being able to see the background still, it is shrunk down to be able to fit everything in. We have some additional other elements, so we have the elements on the left here. So this information is actually handled by using the PlayHistory class. So it's not rendered by the PlayHistory class, that is actually being rendered by the postgame window as well. But the PlayHistory is actually keeping track of that information. So when there's a change to it, obviously it'll be reflected when we open up this window. We also have a share button, which is obviously being rendered by the PostGameWnd, and the button is going to just be using the button class. And then similarly, we have another 2 buttons at the bottom here. So there's 3 buttons that appear as part of this overall interface. Now you'll see that we have in the middle here this section with the information for the histogram. Obviously, because we haven't actually won anything or anything like that for any of this yet, because we've only played 1 game, the histogram's not going to actually show any bars at all, and that'll still be showing a 0. But what this is handled by is the horizontal histogram. And so the horizontal histogram class is handling the overall presentation of the entire histogram, and then the individual bars, those are being handled by the HistogramBar class. So we've got the HistogramBar class over here, and so that is handling all of that information. So in terms of the other classes then, so if we just talk about each of those, I'll just get rid of the other markers out of the way. So the ones we haven't talked about yet as being part of an interface at all. So we have the game class, we have the SFMLGame class, we have the WndInterface class, we have the WordDatabase Class, and we also actually have the main file. So all of these have matching CPP files, except that the WndInterface does not have a matching CPP file because it's just a definition of an abstract class, and it's not actually sort of creating anything that needs to be defined inside a CPP file. And then we have the main file as a separate one because obviously we don't need to provide any additional classes. So what we actually have here is that the SFMLGame class is containing all of the information about running the game loop and making sure that that's ticking on and receiving all of the events about pressing the mouse or moving the mouse or touching the keyboard in different ways. And that then passes the information on to the game class. So the game class is implementing our specific implementation of the game, and so that is then being able to handle how the windows are shown, what windows are shown, and then being able to show multiple windows at the same time, that sort of stuff. and it then passes the information on to whichever windows are currently open. So if there's currently the overlay that's up at the time, which is the post-game screen, it'll be passing the events for interaction to that window, or if there's no overlay up, it would be passing events to the core game in the PuzzleWnd. So we'll look at that in code in a moment. But the other classes, so WndInterface, this is basically just a generic implementation of being able to represent the information about a window or object that is part of a window. And so it includes stuff like being able to keep track of the dimensions of that element, and some additional information for interfacing with the class, so being able to call a generic draw function, and also being able to call sort of like update and functions for passing the information about button presses, key presses, that sort of stuff. WordDatabase is used by the PuzzleWnd to randomly select a word. And so that selects a word and then shows it as part of that window. I actually might be part of game, sorry. So we'll look at that in a moment. But essentially, the game will give the PuzzleWnd a word, and that word is then what's displayed as part of the window. And so when we go to the next game, it'll recreate the window ready for that new word. And so finally, the last one is the main.cpp, and so that's the simplest file. Essentially, that's just creating the instance of our SFMLGame, and that is then calling to basically begin looping until the game ends. Okay, so if we go through some of the files, so the entry point for the program, we have just this simple, we include the SFMLGame class, and we basically just create our game object and then tell it to loop, and then once that game loop is ended, then we just exit. So inside the SFMLGame class, so we'll look first of all at the H file. So inside of this SFML class, we're going to just have an initialization part. We don't actually do anything for the destruction because it's all handled automatically. And we just have the definition of the game loop method. So as part of this, we maintain the window that is being rendered to. We keep a reference to the font that we're using for all of the text throughout the game. We have a reference to our game object that we're passing our events to, and we have a method to be able to load the font in. So as part of the implementation of this class, first of all, when we load in the font, so we just have our standard sort of creating the font, we load or attempt to load in the font. If it fails, it'll throw out an error at us, otherwise it'll just return the font back to us. But essentially, we create in our constructor all of the objects we need. So we create our window, which is going to have a fixed width and height, so the 1280 by 720. So you could easily change that to be different, but you would need to possibly change some of the math to make it scale properly if you were to do that. And so to be able to make it so it can't be resized, we have these set so that it will flag to remove the ability to resize or maximize or anything like that. And so then it also loads the font, it initializes the game object, and it passes that font to the game object. Then once we're actually ready for our game to loop, essentially it's just going to have a clock that's set up. This is to be able to track how long is between each of the loops of our game. So essentially we loop while there is still the game open. So if the user closes the window, then obviously this loop will terminate, and we can also close it from within the events here. So we just basically get the amount of time that has elapsed since the last loop, and so this will give us the step time from that period. So this is very useful because it's allowing you in some games to be able to sort of display animations. We're not really using the delta time in this particular game for any of the functionality. It's all based on just the events occurring. But if you were to be writing a game that had any sort of animation and you wanted to use the time, you would need to use this delta time to be able to get that information and then use it as part of your math to animate. So we have that it polls all of the events that are currently there. So the events include all sorts of different things, but for specifically this game, we're looking at the close event. So this happens if the user clicks on the close button. It will then just tell it to close the window. We could also handle some sort of, are you sure you want to close in this kind of area? But for the purpose of this game, we're not actually going to worry about preventing the game from just closing immediately. We also handle the mouse button pressed. So this is when the user clicks down, and you can see that we're actually passing it off to a method inside of our game object that will handle that press, and we just pass it a vector with 2 integers, and we essentially pass it whether or not it was a left mouse or a right mouse. Anything that's not a left mouse is considered to be right in the case of this code. Then we have the mouse moved. So the difference between these two, so mouse pressed is when we're clicking on one of the buttons or clicking on one of the letters or that sort of thing. Then the mouse moved, this is for being able to have any of the hovering effects. So for the buttons, we can have that we hover over them perhaps, and that would allow us to check when the mouse is moved, if it's moved in or out of the object. And finally, the other event is key press. So whenever any key is pressed, we just pass that key that was pressed onto our game object as well. And so after all of the events that have happened, so there could be multiple events that have occurred, once all of those are handled, we tell the game to update, and we pass over the current amount of time since the last update, and then we just do the rendering. So we clear it with a black background, so you could change the color here if you wanted a different color for the entire background. Then we draw all of the game's window, we tell it to display what was drawn, and then we can just check if it should be closing and to close it if necessary. Alright, so moving on to the next class. So the game class is the next one down. So for the game class, we're passing all of those messages from the SFML class. And so the purpose of this class is that we're going to be essentially managing all of the windows and passing events to the windows as necessary. So the windows in this case are going to be the PuzzleWnd and the PostGameWnd. So when we create the game, we're going to be passing in the bounds for the game, so essentially the play space, and we also pass in the font. So these are the 2 prerequisites to being able to initialize the game. And then we just have another few methods to be able to handle the different actions within the game. So we have an update method. Essentially this is going to update each of the windows that are currently active. We have a draw to draw all of the windows onto the screen, and then we have other methods to be able to pass the input onto those windows. And we also have the method here to be able to check whether or not the quit button has been clicked, essentially. So if the quit button was clicked, this will be returning true, and then back in the SFML game class here, this would be true and let it quit at that point. And then in terms of the data we're storing here, so we're storing the bounds and the font, which are passed to the class. We're also storing a random engine, and so this random engine is letting us select randomly the words from our database. And so this is basically being passed over to the database to use that for all the randomization. Then we have two windows, and so we have the active interface and the active overlay. So the active interface in this case is always going to be the PuzzleWnd, and then the active overlay in this case is always, if there is one, going to be the PostGameWnd. For the purpose of this program, as it is, the active interface will never not have something assigned to it when it gets to an action, but the active overlay could be null. And essentially, whenever we switch the interface to a new one, it would be deleting the old one to replace it with the new one. So we have our Boolean variable to be able to track when the player has pressed quit, and so it would store true into the terminate game variable when that occurs. We have our reference to the word database using a unique pointer, and we have a reference to our play history. So as we play games, it will continually update the history with additional wins or losses or whatever our score is as we go. So if we look inside what actually happens in the main, the methods of the class. So when we initialize this class, we initialize our random engine, and so we're using the random class with the chrono class to be able to get a random seed essentially based on the time, and then using that seed we're then initializing our random engine, and we pass that to our word database, and we tell it also where our play history is saved. We initialize both of the interfaces to initially not point to anything, but we do create right away an interface that is the PuzzleWnd. And you can see here, as I was saying before, we're going to use our word database to get a random word. So we will look at the word database next after this class, and we'll talk about what's in that. So when we delete this interface, we're going to need to delete the active interface because that one is not handled when we're doing the swap. So it needs to make sure that it deletes that, otherwise we'll just have a memory leak. Inside of our update, so this could probably be simplified if we swapped our pointers to be using like a unique pointer instead of just a raw pointer. So it's something that could be changed if you want to try and make that change yourself. But essentially what we have here is that we check if we have an overlay, and if we do have an overlay, then it will call the update on our overlay, and based on the result of that overlay, so if it gives the result that we want to restart, so that's where they've pressed the new word button. If they've pressed the new word button, then it's going to delete the overlay and set it to a null pointer. Then we delete the active interface and we initialize a new PuzzleWnd interface with a new random word. If the user clicks the quit button, so if the result state of the overlay is quit, then we would terminate game by setting the boolean variable terminate game to true. So if we don't have this overlay visible, then we will check if the active interface is available. So normally this is pretty much always going to be true. There shouldn't be a case where it's not true. So it should always be that if the active overlay is not there, it will perform an update on the active interface. So a very similar kind of process where it updates the active interface and then it's going to check if the result of that window was that it's finished. So the finished state is where you're either solving it successfully by entering the correct word, or you've used up all of your guesses, and so that will change the result there. We get the GuessGrid. So once we have finished the actual game, we're needing to get the information to pass on to the overlay interface that we're creating. So to be able to do that, we get the GuessGrid, we get the whatever the rules were, which is essentially the information about sort of all of the attempts you made, and that's pulled out of the GuessGrid. And then the solution is also grabbed. So we have the solution that was posed to the user, and so to be able to show that, we're passing it on to the user. And you can see here that at this point, we're then checking if the user actually solved the solution. If they did solve it, then we insert at the number of rules that were used to be able to solve it, -1. So what this is going to do is that if you took one attempt, then it's going to insert at position 0. If you took 2 attempts, it'll insert position 1, and so on. So essentially this is going to change the count for the number of attempts it took, so that if you had 1 attempt, it'll actually map it to 0, so we can store it nicely into our array of results for the histogram. And we also have the insert history loss, so this is just being able to increase the number of attempts, and it modifies obviously the win percent when you've played more games but not won them all. Then once we've generated all of this information, pulling it out of the active interface, we just get the active overlay we create as a postgame window, and we pass it all of the information that it needs. So we pass it the bounds, we pass it the font, we pass it what the solution was, we pass whether it was solved, we pass the number of attempts that it took, we pass the information about the history of what's been played in previous games, and we also pass the what the share string is. So this is what happens for what's copied to the clipboard when you press share. So that's pre-generated once, and so it doesn't matter how many times you click share, it's just going to already have that information ready, pre-generated. So that's the update. Then we have the draw and the other functions. So essentially all of these other functions are going to just be checking if the elements are null, and then if they're not null, it'll draw or whatever. So in the case of drawing, it will always draw the active interface at the back, and then it'll always draw the overlay at the front. So the first element that's listed here will obviously be at the back, and the second element will be at the front. For the handling of the other three events though, you'll notice that each of these use an else if instead of just ifs for each of these. So this is how we constrain it so that if the overlay is currently active, it'll only pass to the overlay. But if the overlay is not active, then it'll pass the event onto the other interface. Then we have the same thing for the move and the key press, so there's not really any difference there. And the terminate game variable is what's returned when we get that get game close requested. So moving on to the word database, as I said, was going to be next. So the word database is quite simple. It actually has a method here we're not using. So it has an isValidWord method. We don't actually use that in this application. If you were wanting to allow only valid words that are part of the dictionary to be entered as attempts, then you could check using this function if the word is valid, and it would tell you yes or no with a true or false. Essentially though, we're passing the random engine over, and that is what we use to select the words, and we use that inside of our getRandomWord method. We have our entire collection of words just read into a vector, and we have a method called loadDatabase, which just loads all of that in from a file. So if we look at the implementation, the constructor essentially just stores the random engine as the reference, and then we call loadDatabase, which is going to initialize all of the words in there. So to be able to initialize all the words, we just open the file using ifstream, and so that could be wherever you want it to be. It doesn't necessarily have to be up one level at the words.txt. You could also preload it into the code as an array or something if you really wanted to. But by having it in a file, it allows you to easily modify and change as you want at any time if you wanted to shrink or increase the number of words that are available. So obviously if there's an error with opening the file, it'll give an error. Then we just loop through for every line in the file, so each of the lines is a separate word. We're then just making everything uppercase to be able to simplify the presentation, and we're just putting it onto the back of the vector. Then we close the file and we give an error output if there were no words read in. So if you supply an empty file, it'll show an error, but this isn't necessary if you can ensure that there's definitely going to be some words, or you could provide a fallback where it provides a subset of a few other words as a backup. But essentially you could also generate the file from scratch, just have a bit of code that makes the file appear and populates it. But if you're doing that, then you could just as easily write all of the elements to be loaded in hard-coded anyway, so you may not want to do that. Then we sort the database, and this allows us, so if we wanted to search it efficiently, it would then be sorted alphanumerically. To be able to get the random words, all we do is get a word at, and then we get a position based on the size, the number of elements that are in there. And if we want to check if a word is valid, we can just perform a find, and we just find the word or not, essentially. Alright, so now that we've gone through briefly what game does and the word database does, the next thing to do is to look at how the PuzzleWnd is set up. So it'll look very similar. So of course we're extending from the WndInterface, and so we'll look at that just briefly as the next thing. But essentially we're taking in the bounds of our window, we're taking in the font to be able to draw the text, and we're taking in the solution that we're supposed to be solving. We have the overrides for all of the functions, so we have the ability to handle an update, a draw, a mouse press, a mouse move, and a keyboard. And then there's just two additional methods to be able to get the state externally. So we have the getGuessGrid, and this just returns a reference to the GuessGrid, and then we also have the result state, which is to be able to tell when the puzzle is either solved or at a point where you can no longer solve it because you filled all of the attempts. As part of the variables we're storing here, so we just store the reference to the font. We also store the information that appears in the top left. So that was the Wordle by Peter Mitchell. So that appears based on these two text variables. Then we have a KeyboardWnd, which is storing the keyboard that appears at the bottom of the screen. We have the GuessGrid, which shows all of the guesses, and we store our result state, which tells us whether or not the puzzle has been solved or failed. And so if we look inside of the PuzzleWnd, so if we go to PuzzleWnd and just look at what it does inside of here, so you can see that we start by initializing all of our variables, which includes having our WndInterface takes the bounds in. Then we have our font stored. We create our title, which is the large size 50 Wordle text, and then the by Peter Mitchell appears in size 15 text. Then we have our keyboard object, which is using the bounds and the font, and so it actually does shrink itself down. You could modify it so it takes in a particular size and auto scales, but it's essentially just using this for positioning, and it knows how big it can be. And similar thing for the GuessGrid. It also takes in what the solution is, and then how many letters are being, the number of attempts that are allowed. So you could increase the number of attempts, you could shrink the number of attempts, but essentially 6 is the number of rows that appear in the GuessGrid. And so we initialize it by setting the positions of the text. This is just setting the Wordle and by Peter Mitchell to the correct positions. And so this is sort of 5 down and 5 across, and then 5 across and just enough down that it's appearing 10 pixels after the bottom of Wordle. So because the size of the font is 50, then we know that it needs to be 50 down, and so then we can offset by the amount that was offset by for the title, and then if we want it 10 after that, we'd have 10 added as well. So you could change that to be whatever sort of distance between them. The destructor does nothing here, we don't actually need it to do anything. Our update essentially just checks whether or not the game is over. So if the GuessGrid tells it that it's solved, or it's run out of guesses, then it changes to finished, but it doesn't necessarily do anything else there. For our drawing, we just draw both of the text elements that appear in the top left, and then we just draw the keyboard and the GuessGrid. For handling the press, we first of all pass off the mouse press to the keyboard. So if the user has clicked on the keyboard, it'll handle that. And if that was something that happened, then it will essentially make the result of the action ID -1 if nothing was pressed, or another number if something was pressed. Now the number that it returns is going to be either the character code for a letter, or it will be the back arrow for the backspace, or it'll be 1 for the check button where you're attempting to submit a solution. The check solution is going to perform the check and validate based on the GuessGrid, and it'll try and do the backspace with removing a letter with the GuessGrid as well, and then otherwise it's if it wasn't the backspace or the check, it would try and insert whatever the letter. So this will obviously fail if the letter isn't on the right range. We'll look at that when we get to the GuessGrid. Essentially we cast the action into a char type, and that then allows us to immediately use it as if it was a letter when we're handling it in that class. For the mouse move, we just basically pass to the keyboard class the handle mouse move, and we don't really care about that at all for in PuzzleWnd. Similarly, for the handle key input, we just pass off to our GuessGrid with the handle key input with whatever the key is. And so if a key was pressed, then we would apply whatever the rule is that has been applied. So this is happening when we press the check button or press enter, and so that will mean that it will change the color of the keyboard to apply those colors based on the rules. So if something has been matched to a correct position, it'll always be green. Otherwise, it will change it to yellow if there's something in the wrong position, or otherwise grey if it was not anywhere in the solution. So in terms of the other methods here, we're just passing back the values of those two other variables. So the GuessGrid and the current state allows us to essentially just pass that information back to the game class for when it needs to create the PostGameWnd. So the next one that we're going to look at is the WndInterface. So this class essentially just defines the abstract class for all of the methods that are shared between all of the WND classes. So it also defines the result states. So we don't actually use all of these result states in this application, but the default would be nothing. So this would just be if there's no current result that's necessary to handle yet. If the window is finished, then it would be finished. If we want to restart, this could be like restarting a level, restarting a game, it could be all sorts of things, but it's just some sort of restart operation based on the current context. If we want to display a menu, we don't actually use the menu in this case. We also don't use the restart. But the other one that we do use is quit. So when you click the quit button as part of the postgame interface, it'll use that to be able to perform a quit. So you'll see that as part of this class, we have a bounds that's stored. We also store if the interface is enabled. You could have that it's disabled and make it sort of not do certain things. In this particular application, we're not using that at all, but it is a property you can use. The next few methods are all defined as so update and draw have to be implemented as part of all window classes. So they default to being pure virtual functions, so that forces it onto those classes that extend this class. But the other functions don't have to be implemented. So you can just override the default nothing behavior of the handling of key input, mouse presses, and mouse moving. And then there's other functions which let you set enabled, check if it's enabled, and then get the result state. So the default for the result state, if you don't override this function, is that it'll just be nothing state. So if you want to use this, you would need to override it, which is happening inside of both the PuzzleWnd and also the PostGameWnd. Alright, and so essentially we're just storing in here the isEnabled and the bounds, which are then used for whatever the object is. And you'll notice that it's protected. This means that any object that's extending this has access to that information, but it's private to any external party. Alright, so the next part we want to probably look at is the keyboard. So if we just go to the keyboard class. So for the keyboard class, we're essentially defining it again with the bounds and the font. And we have a no update. So we just override it with an empty update method. We don't actually need to do anything during the update each time. But we do have a draw method, and we also override the press, the move, and we don't actually override the key press here, because that's just handled by the PuzzleWnd by passing directly into the GuessGrid. So we also have this getActionID reset, and we'll look at what that does in a moment, but essentially we get the action and then it resets the default. And we also have apply rules, which is allowing us to color based on whatever the rules are. As part of the interface, we're storing a collection of buttons. So the next class we'll look at will be the button class to talk about what that does and how it works. But we also store as part of our class whatever the action ID of the latest pressed button is. And that allows us to pass that information over to the GuessGrid. And we have a function to initialize all the buttons. Okay, so now if we look at the CPP file for the keyboard, so the initialization for the constructor essentially initializes all the buttons, which we'll get to at the bottom, but initializes the action ID to -1 as the default. Then we have that the draw essentially iterates through all of the buttons by reference, and so it'll just call the draw function on each of those. And then similarly for the handle mouse press, we just check for every button if the button has the mouse position inside it. If there is a button that's been clicked on, then we would set the action ID to whatever the button's ID is, and then break out of our loop. So if we've clicked on a button, we don't need to check the other buttons. But we can then, for the mouse moved, we can check for setting the hovering state. So as you hover over or move out again, it's a very similar thing. So we just check if the position of the mouse is inside of that button, and we just use that as a true or false to set whether or not we're currently hovering over that button. And so that just creates the effect to be able to show that there's interaction happening. So the getActionID reset, so we just store the old action ID, before we reset it with whatever the current action ID is. And that allows us then to reset that value back to the -1, which essentially represents a no action. And we have the returning of that old action ID. So this just lets us, each time we call this method, we're just then handling one action, and it'll then just continually only provide actions one at a time, which it would be impossible to provide multiple actions from the keyboard. You would have to be clicking faster than the update rate, which it would be very difficult unless you have a very slow computer or you're deliberately manipulating it to stop it sort of working properly in some sort of way. Alright, so then we have the apply rules, where it has to go through and apply colors to each of the elements. So essentially what we do is we just go for every rule, then we loop through for every position in the rule, and then we just check whether or not it's supposed to have a correct position or wrong position, but does appear somewhere in the string, and we apply by finding the button that matches that, and then we try to apply the color. So we only apply the color dependent on a rule. So the we apply it based on, I think inside of the apply color ID, it actually checks before trying to change it, which we'll look in a moment at. But yeah, when we get to the button, it will not override, say for example, if you set the color to green, and then you had another different pattern where you tried to enter a different word entirely, it shouldn't then change to yellow if you've previously entered a correct position. So for being able to generate the entire keyboard, we actually just have a vector initialized with all of the letters in order, and then we just have a bit of math to work out the position for centering all of the elements, and then essentially just loop through and position all of the elements by inserting them at the back of the vector. And so we have first of all the top row, which loops through the first 10 elements, then the middle row, and then the bottom row. And we do have the special case for check because it's a larger button. So all of the other buttons have a simple width, but the check button has an increased width. So it's not handled automatically based on the width of the text, it's just pre-calculated and put in. So that's handled just by the button width that we have here. Okay, so now if we go on to actually look at the definition of a button. So in the button class, essentially we're just defining a button that is made up of some set of bounds. This is the space in which you can click on the button and where the button will be shown visually. Then we have the text that is shown on the button. We have whatever the action ID is that's represented when we press the button, some sort of unique ID inside the button that is going to tell it what to do with that press. And then we have a font to be able to render the text. So we just have the draw, we have the get action ID, we have a method to set whether or not it's hovering, we have our method to be able to check if the position is inside, we have a method to set the background color, we have a method to apply the color ID, and then we have some variables that will store the information about the button. So we have our bounds, we have our action ID, we have a boolean to tell us whether or not it's hovered, we have our text that is displayed on the button, we have our visual of what the text is, we have the rectangle that shows as the background, and we have an ID to represent what the color of that background is, so we can know for how it's supposed to be changed. So if we look in the CPP file, when we initialize the button, we actually set a fair few properties. So we initialize the bounds, the text, and the action ID just to the plain properties. The background element is set to have the width and height such that it's -2 from the sizes, because we're going to have a border that's 1 pixel wide going all the way around, so we need to subtract 2 from that width and height. We have a text visual, which is just going to be set to the text with the font and size 30. And then we set a number of other properties for the text. So the text is being set to initially have white color, be bold, and we move the position to be inside the centered position of the button. So it'll try and center it. And so we do that by taking the left side as the side of the button. Then we add the middle of the button, and then we subtract to remove half the width of the text. So if the text was wider than the button, this would give us trailing over both sides of the button. So you could take into account that and either scale the size of the text, perhaps, or make it so that the button size will increase if you really wanted to handle those cases. But for this, we're sort of basically hard coding the size of the buttons for simplicity. We're also then setting the background's properties, so the position of the background is shifted to, again, the down one and across one, and this is essentially to handle there being a border around. And so the way we set that border is we set the outline thickness. So we just have a border of 1 and then the color white for the border. And so the fill color is basically black, very, very close to black. It's just very slightly gray. So if it was 0, 0, 0, that would be black entirely, so it's just very slightly different. For rendering the button, we draw the background first and then the text on top. For getting the action ID, it's just whatever is stored is returned. For changing the hovering state, we change the state to the is hovering, and then we just check. If it is hovering, then we either change to a 3 pixel border, or we just change it to 1 pixel. So if it's hovered, it'll increase the size of the border by 2 pixels all the way around, or otherwise it'll just stay at the 1 pixel, and it'll change back and forward depending on whether or not the user's hovering at any particular time. So the next part we have is if it's inside, we can just use the contains method that's part of the interact class for SFML, and that'll tell us whether or not the position is inside of a bounds. For being able to set the background color of our element, we can just call the background set fill color. And so then we just need to have the reason we have this is for being able to change the default properties for the share button. That button in particular has slightly different appearance because it has the green background, and so that's used here to be able to change that on the PostGameWnd. For being able to apply the color ID, so this is going to conditionally change the color ID. So it's not going to set the color unless the color ID is greater than whatever the current color ID is. So that means that if we're setting to, so this one would be the green, this would be the yellow, and then this one would be the gray color. So if you're not setting, if it's already green, then it will never change the color again. But if it was, for example, initially the gray color, then it will change it to any of the others. Unless you're just trying to change it to the gray again. So if you were setting to a color ID of 1, then it would not change it either. Okay, so that's all of the stuff for the button class. So we'll look next at the play history, just so we can look at that before we move on to the other elements. So the play history, this stores the information about the number of wins and the streak that they're on and that sort of information. And so essentially it contains a list of pairs for the history with the number of wins of each number of guesses. And so you have the number of played total, you have the total number of won, the number of wins in a row, the best number of wins you've ever had in a row, where the file is stored, and then some methods for loading and saving the file, and initializing defaults if the file doesn't exist. For being able to manage this class, we have the constructor where it takes in the file name that it's going to use for the history. We have a method to be able to insert into our history that takes the whatever the count is that we need to increment. We have a method to be able to insert for the loss events. We have a method to be able to get the full history if we need to. We have also methods to get the total played, the current streak, the max streak, and the win percent. And so each of these is used to either insert the results of a game or to get the results of a game from the history. So when we've won our game, we would be passing the information across as we showed inside of the game class. So if we look inside of the CPP file for play history, when we create our play history, we just call load file, and this is going to load the file by a process of initially checking that it opened properly. If it didn't open properly, it'll initialize defaults, or if at any other point it fails, it will initialize defaults, and then it will go through and read in all of the key and values for the sort of 1 attempt, 2 attempt, 3 attempt, and so on, for how many of those there were of each, and then it'll insert all of those into our vector, and all of the other information is read in as well. And so if any of that fails, it just initializes defaults. So we should look at what initialize default does. Initialize default just sets everything to 0 for the 0 to 6, 0 to 5, so the 1 to 6 attempts, and then 0s for everything else, obviously. So if you haven't played it all, then it's not going to have any data about that. So essentially, for the rest of the stuff we have here, when we're inserting into our history, we check first of all that there's a valid number that's being passed in. If somehow an invalid number came through, which shouldn't happen based on the way the game is coded, but if there was modification to the classes that happened that somehow caused data to be passed improperly, it stops it from being processed. Then we increment the stats for winning. So if you've won the game, this is what's being called. So we increase the number of total wins, we increase the number of total played, and we increase the streak. And then we check if the streak that we're on is larger than whatever our maximum streak was. And if it is, then we change that. Then we get whatever the position is for that win. So like if you did it in 3, then it would, at the position related to doing it in 3 attempts, it'll increase the number of times that's happened. So second here refers to the number of times, and if you were to have first, it would be referring to what the value is for the number of attempts that it would have taken. And then we just save that to our file. Similarly, for the insert loss, we don't need to have any check, so we're not calling sort of any with value passed to it, so we just need to increase the number of played. We reset our streak, so obviously if we've lost it, then we lose our current streak, and then we just save. For the other accessor methods, essentially we're just returning the history of various types, and then the win percent is calculated. So we get the total one, we multiply it by 100, and then we just divide by the total played, and that gives us a like up to 100% or down to 0%. And then for the saving, we just have that it opens the file as an output file stream, and then we just loop through for every element of our collection of data, and we just dump those into the file, and we just dump all of the rest into the file. So the same order that was read in is what it's being put out as. Okay, so the last of the classes that's relevant, actually not the last class, we've got 2 other classes to go through. So the 2 classes that are still to be done for the relevant to the puzzle are the GuessGrid and the PuzzleLetter. So we'll look at GuessGrid, and then we'll look at the PuzzleLetter class and how they're implemented. So the GuessGrid essentially takes in the bounds, the font, the whatever the solution is, and the number of guesses allowed, and it does nothing for updating, doesn't need to. It will draw, obviously, which will draw the grid of the puzzle letters. It will handle whenever there's a key press to simulate an attempt to insert a letter. It has the try insert letter, which only does something if it's a valid letter, or if there's space to be able to insert a letter. There's the method for the backspace, the check solution, checking if it is solved, if there are more guesses, a method to get what the rules are, getting whatever the key was that was pressed. If the check result is one thing or another, and the getting the solutions. This is for when you're wanting to sort of generate the post-game interface. You need to use the solution, and then there's the share string, which is the string that's made up based on what you need to be able to share, say in like Facebook or Discord or whatever, the results you got. As part of this interface, we have just the basically a 2D vector of letters. We have the whichever the position is currently for insertion. We have whatever the index is for the word. So essentially it goes down one row at a time, and then the position inside of the row where you're up to. We have a boolean to show whether or not it's currently solved. Obviously if it's solved, it's not going to be continuing to update anymore. And then if you used key to check, this means you've pressed the check button and it should perform the check. And then there's storing the solution and the initializing the base state of all of the visuals inside of this element. So if we look inside of the GuessGrid, so the initialization pretty much initializes all of the grid inside of initialize all guesses, and it just initializes not being solved at the first position of the first word. And obviously you haven't used the check key initially. When you're drawing, it's just looping through for every one of the letters, and it's going to draw each of those boxes with or without the letters by using the PuzzleLetter class. For the handling the key input with the GuessGrid, essentially it's doing something very similar to what happens when we're doing the pressing on the buttons. It's going to check whatever the key code is and turn it into an int, and then it's going to check if it's in a valid range. If it is in a valid range, it'll try and insert the letter by casting it back to a character, or otherwise it will try and check if it's a backspace or you've pressed enter, and that'll handle removing letters or checking if the solution is correct. And in this case, because we've clicked using the keyboard, we actually do need to flag that we've used that key so that it knows to be able to perform the update on that check. Attempting to insert the letter, we just check first of all if there's still room to be still a word that we're supposed to be trying to insert at. If we have not currently solved it, so this is actually the reverse. So if we've already filled up the maximum number of words, if we've already solved it, if we don't have room to insert at the current word, then we just don't insert at all. Otherwise, it will try and set the letter at the position, so it just gets the lookup of the current word, and then for the current word, it'll insert at whatever the position in that word is with whatever the letter is, and then it just moves to the next position. The backspace is handled in a similar way, where we check and do nothing if it was already solved. If we're already at the beginning of the word, we can't continue to backspace, so you can't go back to previous attempts, for example. And if we've already filled the maximum number of attempts, we can't sort of do anything anyway either. So if we then move back one for the position, and we just basically clear that position to set it to an empty character. For checking, it's a little bit more complicated because we're generating the wrong position and all that information. So essentially we have, first of all, a similar check where we're checking that it's if it's already solved, or if there's if it's not filled, so you need the word to be entirely filled to check it, then it will return. Then we have a counter to be able to say how many of the letters are entirely correct. So this lets you know at the end whether or not the entire solution has been solved. But essentially we loop through for every letter in the solution. We're checking by getting whatever the guessed letter is. So it gets the letter at that position, and then we check if the guess matches the solution. If it does, then we would set the solution state of that letter to show as correct. That essentially means that it's going to become green, and we would increase the count of how many we've successfully solved. Then we're checking, because this is the handling of if it is correct, we then need to check if it is somewhere else in the solution for that letter. So we first of all go through and find if the guess appears for a number of times within the solution. And so if it appears anywhere in the solution, we check that the positions where it should be matched are already matched, and then we position only colors where it's going to be essentially the first position. So if you had, for example, you'd use two E's, but only one of those should be there. If you already had one in the correct position, it'll just color that one green, and it won't color another one. But if you have two and there's only supposed to be one, and they're both in the wrong position, then it would cover the leftmost one to be the yellow. And so that's essentially what this code here is doing. It's checking through and it's basically validating whether or not there should be a certain number of elements that are colored. And then it colors by setting either to wrong pos or no state. So wrong pos is the yellow and no state is the gray. And then, so there's essentially two situations where it can be the gray. So if it shouldn't have any of the letter, then we can just skip immediately to the no state. But if we go through and find that it's in the wrong position and it should be colored, this would be the yellow. But if we got, for example, a case where there's still more, that we've got excess letters of that type, then it'll show up as gray with this no state. So that sort of state where we're talking about with the multiple E's, where you've got two and there's, it would color the leftmost one yellow if they would both be yellow. Alright, so after it's done that, it will, after it's looped through every position of the solution, it'll move to the next word, and it will move the position for insertion to the beginning of the word again, and then it will check if the length is equal to the solution count, so the number of ones that were matched as being green. If it is a match, then obviously it's solved. And so is solved returns the value of the solved variable. Then we have, if there are more guesses, that's just checking if there's still more positions empty in the array. Basically, if you haven't filled up the entire number of 6 with solved answers yet. And then we have a get all rules method. Now, the purpose of this, it's very similar to the one that I wrote for being able to have the other program where you're processing and working out the sort of entering of a rule, where you enter the rules in with stars and hashes. You can see my other video where I did a demo where it shows the other application, but essentially you'd enter a rule where a star precedes the letter, and that would mean that the letter that's following it is in the correct position. Or if you had a hash and then a letter, that letter that's following would be in the wrong position, but it appears somewhere in the word. Okay, so essentially it generates the combination of letters with the stars and hashes based on whatever the correct or wrong pos values are, and then it just outputs it into a string, yeah, just a collection of strings. And so this contains then, what we're returning is essentially just all of the rules based on all of the attempts. So you could use this to be able to evaluate a guess of whatever the information is for an AI if you were to be guessing it within this game. But essentially, this allows us to just easily color the puzzle letters based on the keyboard, as we were showing before, using the rules that are being passed from here. Then we have a very similar thing to what we did with the keyboard, where we just have the variable we're returning stored into a temporary result, and then we reset that back to the default state, so this is false in this case, and then we return the result. So this would become true and we just hit enter and we actually perform a check where it's a valid check, and we just then return whether or not we've pressed that button, so that it knows that it's supposed to perform the necessary steps. Getting the solution just returns the string with the solution in it. Getting the share string, essentially it just creates a string stream that's then output as a message at the very end as a string, and so it just contains a custom message where it's sort of got Peter's custom Wordle game, and then the sort of solution, sort of whether or not you succeeded, followed by whatever the word is for the solution, followed by whether or not you solved it, number of attempts out of 6 you took, and then obviously the green, yellow, and black squares are output for the entire grid as necessary. And so this doesn't actually output anything here, but it generates a string that you're then able to copy to the clipboard with a share button, which we'll get to with the PostGameWnd when I go through that. But essentially the other method that we have here is the initialize all guesses. So initialize all guesses basically does a similar thing to the initialization of the keyboard. We just initialize some properties to know where everything should be and offsets that we need to use, and then just loop through for the number of guesses we're allowing and just the number of elements in each row, and it just populates all of those with new puzzle letter objects that are positioned correctly. Alright, so it's probably time we look at PuzzleLetter. So PuzzleLetter is quite similar to the button in the way that it actually works, but the main difference is that we can set the solution state. We can also get and set the letter, and that allows us to change the properties. So we have initializing it with just the bounds of the puzzle letter, the font, and we have a draw, which is going to draw the rectangle and the letter. We have the get letter to be able to tell us what the letter is that's currently part of this puzzle that's been attempted as an entry. We have something to be able to set whatever the letter is, because initially it's going to be empty with a blank space. We have the ability to set whatever the solution state is, which is going to be like the no state, correct, or wrong pos, to be able to set the color. And then we have getting whatever the solution state is, which is useful for some of those methods we were just looking at. Then we store the bounds, we store whatever the letter is that's being represented here, we store something for the background to be able to draw the rectangle, we have something for the text to be able to store it, we have whatever the solution state is currently, and a method to set the background. So if we look at the CPP file for PuzzleLetter, then we can see that we just initialize all of the visual elements in the constructor. So we set the background to similar kind of thing with it's going to have a border of 1 pixel around it. So we need to -2 from the bounds, and then we have the 30 for the size, and we do initialize it to A here, but it gets changed to set the string just here to be the space. It's going to have white for the text, it's bold, it positions it central within the bounds, it sets the position of the bounds for the background color to a grayish color, 1 pixel border with a white border. And initially, obviously, it has no state, and that's represented as being the grayish background. So technically, it's not in the background state where it is no state. That only changes when you attempt to submit the solution. But for in terms of the problem, it doesn't actually care about this value until you submit a solution anyway. When we're drawing it, we draw the background and then the text. For getLetter, we're just returning whatever the letter is represented here. Whenever we set the letter, we just change the letter variable, and then we set the text visual to the string of whatever version of whatever we're passing. So it'll convert from the char into a string as necessary. For the set solution state, we don't actually need to check here whether or not we're supposed to be changing it to a color, because this is only going to be called if we are supposed to be changing the color. So we don't need to validate it like we did for the keyboard, but essentially it does the same colors as the keyboard was using, just with a no state, correct, and wrong pos. Then we just have the methods to return the current state and set the background color. Okay, so that's the puzzle letter. So it's fairly simple, it just stores the letter and then just changes the color based on the solution state it's given. I think now we can move on to the PostGameWnd. So the PostGameWnd is a bit more complicated in terms of the amount of data that it's given, because it needs to draw from everything that you've had as part of the game state as we're going through it. So in terms of what we're passing it, we've got the bounds for the entire play space. We have the font that's used for rendering the text. We have the solution for whatever the answer was that we're supposed to have been trying to solve. A variable to show whether or not we won the game. The number of attempts we took to actually complete the game. The history of how well we've done for our previous plays. The share message based on whatever the GuessGrid gave us, and then it's going to use all of the information to generate the interface. So it doesn't do anything for the update, there's no need to, then we have an override for the draw, obviously, because we need to be able to draw everything in the postgame interface. And we handle the press, the move. We don't handle anything to do with the key events because we're not actually handling like pressing escape or whatever. We have an override for the result state because this tells it when we're supposed to be doing a new game or quitting. And then we just store properties for all of the things that are being displayed in this interface. So we have the result state, we have the 3 buttons that are stored in a vector, we have the rectangle shape for the background, we have the rectangle for the full screen background, so it does actually do like a faded partial grey out. So if I bring up the application, we just fail it quickly so you can see the full screen background. So if we just you can see that it grays out the background a little. That is actually a full screen overlay that is happening there with just a very slight alpha that we're passing through. So we have that. We have the title text, which is going to be the text that tells you what's happening for whether or not you won or lost, a solution of what the word was supposed to be, with our reference to a histogram, with our reference to the text showing the total number of played, for the win percent, the current streak, the max streak, and our share string. So we'll look at how that's implemented then. So inside of the PuzzleWnd, there's not very much code because it actually passes off a lot of the jobs to other classes. So we initialize our, not PuzzleGrid, we need PostGame. There's actually quite a lot here. So you can see that it essentially groups into each element being initialized. So we initialize the full screen background. Then we initialize the background, which is going to be that, I think I've got here, so that's the grey, this sort of different grey area here. That's that background, which has a border on it, the white border. Then we have our text showing whether you solved it or better luck next time, which changes color depending on whether or not it's one or the other. And that's centering horizontally in that section. It shows what the solution is with the solution text, and then it adds the buttons, which each have a unique value. So button 0, button 1, button 2 for the action IDs, for the new word, quit, and share. And so then after we initialize all of those, we calculate the position and everything for how the histogram rect should appear. We initialize the histogram, and then we initialize all of the other outputs for whatever the number of played or whatever are supposed to show. So those ones being all of the text on the side over here. Alright, so then for the drawing, we just render out everything. So essentially the background, the smaller background, the title, and all the rest of the text. Then we draw the histogram, then we draw all the buttons, and that handles all of the drawing. And so this would be an overlay, where because the full screen background is transparent, we can see through and see the other active interface behind still. The handling of button presses, essentially when the press happens, we just check for every button in the scene. If the button has the mouse position inside it, then we just check which of the action IDs it is. So if it's action ID of 0, we would set the result state to restart, which essentially means a new word. Or if we have the action ID of 1, that means that we want to set it to quit, because we press the quit button. Or if it's an action ID of 2, then it's getting the share string and just passing it onto the clipboard. So this function here lets you set the clipboard data using the SFML libraries. Then we have a very simple bit for just whenever the mouse moves, it's going to set the hovering state to whether or not the button is inside of that element at the time. And then we just have the result state being returned for whatever it is. So it'll only change based on these, but essentially when the result state changes, it'll either terminate the game or switch to a new word. Alright, so that's the core of the PostGameWnd. So the last parts that we have to look at are the histogram. So we'll look at the histogram bar first. So these are the individual bars. And so essentially this is just having the title text. So the title text is, if I bring this back over, the title text is like this one, for example, here. Then we have the bar, which is represented as being this long bar here. And then we have the last bit is the value text, which is that 0 at the end. And so the 0 is positioned relative to wherever the bar ends. So if the bar was to come to only here, then it would have like a 0 here, for example. So it's not always at the end. So if we look at how that's actually done then in the histogram bar, so essentially it's just setting up a lot of stuff and then just rendering it. So we have the setting up the title text, which is always going to be to the left of the bar. Then we generate the string for whatever the value is, and we use the width of that value to determine how we offset it based on the bar. So we actually calculate the text size first, because if the bar was like 0 size, say for example you had like all of these ones were like maxed out, and then you had a 0 here, so you didn't want to have like a 0 and then just no bar at all. What we're actually doing here is we're having 0 and the bar would come out a little way. So it's going to have an overhang of at least enough to be able to show the whatever numbers are present there. So we use the width of that to place it in, and then we generate the bar based on how it should be positioned to match with whatever fitting needs to happen with the width of the text, and then it just sets the positions of those elements necessary to be able to fill it in. Then for drawing, we just draw the title, which is becoming at the beginning, just like the 1, 2, 3, 4, 5, 6. Then we draw the bar, and then we draw the text on top. And they're being able to set the color, so this is when you've got the one that is your current solve, that shows up as green, and so this lets you change the color to the green, which is what happens inside a histogram's overall sort of horizontal histogram class. So if we go over the horizontal histogram, you see it's even simpler. It just has a collection of bars, and so this collection of bars is initialized by our constructor, and it's drawn by a draw method. So if we look inside of the horizontal histogram class, essentially we have, I'll just make this wider. So essentially we have a fair bit of data being passed over. We have the bounds of our histogram area. We have the font used for the text being printed. We have the data that is being displayed on the histogram. So the left value, or the first value, is the numbers down the side, so the 1, 2, 3, 4, 5, 6, and then this is the frequency of each of those values. So this is the bar length, and this is like each of the different bar IDs, essentially. And then this highlight index is to be able to highlight whatever the solution was, if there was a solution. Essentially we start out by doing a custom compare to be able to find out what the longest bar is going to be. So we get the maximum value out of our vector by comparing the second of each element. So we use the max element standard template library function to search through and find the second value maximum. and then we use that maximum to be able to perform the calculations. So the max is going to determine how far along each bar can go at maximum. Then we have that we're inserting each of the bars, and so each of the bars has that they position on the left. They have a sort of offset based on how far down the bar is, with some additional padding, and then we're just passing in the value to appear as the title, the value to appear as the frequency, and whatever the max is to be able to do the calculations itself inside the bar for how long it should actually be visually. And then to be able to switch the color, so if the highlight index is greater than or equal to 0 and is less than or equal to the bar size, so it'll be -1 if it was a failed attempt, but if it's any other value that's a valid one of the histogram bars, then it will color that bar green essentially. And then for the rendering, we just go through and loop for every bar, we draw it to the window. Alright, so that's the end of going through all of the classes and code and briefly describing it for the Wordle SFML game. If you have any questions, feel free to drop them into the comments below, and I'll try my best to answer any if there are some. And I may at one point sort of make some changes and improve it, and sort of create a walkthrough perhaps, but it is dependent on time whether I can create that sort of content. But let me know if you've liked the video. Do all of the share, comment, subscribe, all that sort of stuff, and I'll hopefully see you in another video. Thank you.